Okay, can I have everybody's attention? We're ready to get started with our talk. There is a sign-in sheet that's floating around, and it's appreciated if you haven't already, if you can sign that. Also, for everybody here, I want to let you know that next week is spring break, so there will not be a speaker next week. We're going to resume the following week, where we're actually having a member of our advisory board giving a talk. This is Katie Mahoney, and she's going to be talking about her work with Schlumberger in the petrochemical industry. For today, we've got Richard Wilkins here. He's coming in to us from Prairie View A&M University, and he's worked with several people out here in this area. So, including Bill. Yeah, including Bill Atwell, who's also a member of our advisory board. And he's going to be talking about space radiation. And also, in case you guys don't know, Prairie View A&M, they have a solar observatory there. They have quite a bit of plasma physics research going on that campus. And so, there are a lot of interesting things that he's going to be telling us about. So I'll turn it over to Bill.
Okay, thank you. Thank you, Dr. Harrison, for having me. Thanks for coming tonight. And so my name is Richard Wilkins. I'm with the Department of Electrical and Computer Engineering at Prairie View A&M. But my background is in physics. I got a PhD from University of Michigan in solid state physics. And so in the electrical engineering department, I teach things like semiconductor physics, things like that, C&M theory, that kind of stuff. And so I am a professor there, and I'm also the director of the Center for Radiation Engineering and Science for Space Exploration. That's the acronym, and I play ice hockey, and so I prefer to call this crease. Crease is the blue area right here where the goalie is, trying to set the net from the puck, and so we'll talk about radiation shielding, and so the goalie there is trying to shield the net, and anyway, you get the idea. Okay, let's see. Just a few words about Prairie View A&M. It is a historically black college and university that was founded just after the Civil War. It's about 45 miles northwest of Houston. Approximately 8,500 students. About 92% of the students are African American. And we offer a Master's of Science and a PhD in Electrical Engineering. It's the only technically oriented PhD that's offered at Prairie View. As far as the NASA CREEP is concerned, it's part of what's called the NASA University Research Center program. It's a program that NASA has had since the early 90s to establish substantial research at historically black schools and also other minority schools to help build up the research infrastructure there. And so I've been involved with these types of programs since about 1995. The emphasis is education through research, both at the undergraduate and graduate levels. And so this is to encourage students towards advanced degrees in STEM disciplines. The idea is then that you would have something on campus that would be able to have students go all the way from freshmen to getting their PhD in the STEM field. One of the nice things about URC is that you can stress very methodical scientific approach, but you also have some flexibility to take advantage of research opportunities that come up. And so, just briefly, I want to, the topic will be tonight is talking about the space radiation research. We live in a radiation environment. As you well know, there's background radiation field here in this room. If I had a Geiger counter set at a reasonable sensitivity and set it on you get the occasional tick in the room, which would be just from any number of sources, including radiation from space. But the Earth has a couple of advantages. Number one, we have a nice atmosphere that acts as a nice radiation field. Also, we have a magnetic field that helps deflect radiation from the surface, and I'll talk a little bit about that But when you go up into space, depending on where you go in space, you have to worry about space radiation for both biological aspects of the astronauts in the space capsule, but also their instrumentation. That's actually more of my area, is more of the radiation effects on electronics and what can happen with those. But we've had since 1985, before my time, there has been space radiation research at Prairie View, and so we've done a number of different things, looking at radiation effects on composites. We've done a lot of radiation shielding, nanotechnology, radiation biology, and one of the things I'll talk just a little bit about is some radiation issues from commercial flight crews. I'm sure there's some frequent flyers in the room, and so we'll talk a little bit about that as well. Okay, so this is a sort of an overview, and I'm not going to talk about this in detail, but what are we doing as far as the center is concerned? We have both experimental and modeling efforts, and again, my area is in the area of rad-hard electronics. Also, we look at radiation dosimetry, multifunctional materials for trying to mitigate the space radiation. You don't really shield space radiation. The energy is just simply too high, but you can try to mitigate it, and so we have different materials we've looked at. We'll talk about some of that. Also in the modeling area, looking at how radiation interacts with materials, and also what the radiation environment is, trying to model that based on your knowledge of what's going on the sun and what is going on out in space with regard to galactic cosmic rays. And so, anyway, basically, going through all this, what we'll talk about is a little bit of look at these experimental test beds, in which we built test beds to try to simulate the surfaces of the Moon and Mars, and try to integrate those in with high-energy particle accelerators to try to simulate as best we can radiation environments in those arenas. So basically, the idea is that, of course, that we want to have safer, more reliable space missions, both for those missions that have human beings on it, and also for space probes. Okay, so again, we'll talk a little bit about all these various things, just touch on some of them, and also I'll give you some results. Okay, so scientists and engineers, when you were looking at the space mission and at different radiation concerns, depending on the type of space mission which you're working in. So again, I'm a physicist, but again, I've been working now with engineers for over 20 years, and so I know some of the things that they worry about. Of course, you have to know what environment you're going to be operating in. If you're operating in the International Space Station, that would be different than if you're operating on the surface of the Moon or Mars. Well, first, spacecraft have a person in it. Obviously, then you have other considerations than you don't. Of course, money comes in, and you want to know exactly how reliable this thing has to be, and of course, that has to do with if there's people or not. Will come back to Earth? Will you have access? Basically, what you're trying to do is you're trying to give some assessment of how much risk you can tolerate for a particular mission, in terms of both the cost and any danger it might be to a human being. So some of the radiation environments, or some of the space environments you have for various missions, obviously you have the Earth orbits, low Earth orbit, where the space station is. Geosynchronous orbit is important for us all because that's where communication satellites are and things that we use all the time. Asteroids have become a target of interest. The Earth-Moon transit, and actually beyond the Moon, for some of the Lagrange points, are now places where the NASA mission folks are looking at perhaps putting a human in the not-too-distant future. And then, of course, the lunar surface, we've already been there, and Martian surface, and interplanetary space, sending probes to places like Europa and some of the moons of Jupiter and other places in the solar system. These are all places where you're going to operate spacecraft and therefore have to worry about the radiation environments in those areas. So this is a nice little sort of a colorful illustration of some of the stuff that we have to worry about in interplanetary space and on the surface of Mars and the Moon, and to some extent here on Earth, you have galactic cosmic rays. Those come from cataclysmic type of processes like supernovae and galaxies colliding and things like that in the universe. And because of the fact that these galactic cosmic rays are essentially the totally ionized nuclei of just about every naturally occurring element that there is. And because of that, that means they have a positive charge, which means that every electric field and magnetic field in the universe pulls and tugs that. And so their directions are fairly randomized with respect to the various directions. And so they come in from all directions in space. Of course, then the biggest source of radiation for our solar system, of course, is the sun. You worry about particularly about solar protons, electrons, and as I mentioned before, the Earth has this very nice magnetic field, which is partly responsible for us all being here. And you can see then that that helps to deflect some of this and redirect it, but it also traps some of it right around the Earth's right around the Earth's vicinity. These are then what we call the Van Allen belts, the trapped radiation belts of the Earth right in this general area. And those are things you have to worry about depending, again, where you're going to put your satellite. Yes, sir.
What are typical uses of solar photons and Van Allen belts?
Well, let's see. In the belt, you have energies generally in the MeV range, but also down the keV, kiloelectron volt. Those are sort of kiloelectron volt up to megaelectron volt. I think typical solar proton is on the order of about 100 MeV, 200 MeV. And we have a real expert here in the audience. Bill is he has to shake his head no. So galactic cosmic rays are different, and I have a chart or two here. Those are very, very high energies. Galactic cosmic rays, as I say, when you're looking at different types of materials you want to make a spacecraft or a habitat out of, you basically have to worry about just mitigating the effects from the galactic cosmic rays. You have a hope of shielding against the solar proton. Okay. And so, anyway, some of the things we'll talk about will revolve around that. So again, what we're interested in as far as the studies of our center is concerned is the risk both for astronauts and for their instrumentation that they would use on a particular mission. The sun, as you may have heard recently, the sun's been in the news, and the reason is because there is a solar cycle, meaning that the activity on the surface of the sun seems to go through an 11-year cycle, from almost no activity to very high activity. Again, this is about an 11-year cycle. Right now, we're probably coming up right about here in the present cycle. So we're going toward what's called the solar maximum, where you have maximum activity. That means that you have the most high probability of getting large amounts of material coming out from the sun, large amounts of radiation from the sun. Most recently, the Curiosity rover has been put down in sleep mode because one of these solar prominences is heading its way. And so the safe thing is to just put it all down, let it ride out the storm, so to speak. And we have very good data on this. This is showing number of sunspots per time. And you can see this goes back all the way, well, maybe you can't see it very well, but this goes back to 1750. Okay? And so people have been looking at this. This particular chart goes up to near 2010, but so we're down here and sort of going up on this one right now. It's not here at the very end. As you can see, we have quite a bit of data on this. The sun has been very regular on this. And so you have the solar maximum, period of peak activity, a lot of stuff in the sun, and solar minimum, the period of low activity. The good thing is that you In the solar minimum, you have less stuff from the sun, but because of the magnetic properties of the sun, you actually have a higher flux of incoming galactic cosmic rays. So it's sort of inverse. If you have a maximum or a minimum of solar radiation, you have a maximum of these galactic cosmic rays that come from outside the solar system, and vice versa. If you have a maximum solar maximum activity, then you have a minimum of the galactic cosmic ray activity. Again, that has to do with the magnetic properties of the sun. I always like this picture because it's very illustrative of the different types of orbits and relative to the radiation belts, the trapped radiation belts. They're called the Van Allen belts. You can see that the low Earth orbit, the LEO, or like the International Space Station is, it's below most of the radiation that's trapped in Earth orbit. And you can also see, fortunately for us, the geo orbits, where our communication satellites are, things like that, so we can watch the NHL network, is up here. And so is a little bit beyond the sun. I'm sorry, beyond the Van Allen belt. But then you can see that depending on what kind of mission you have, for example, maybe a spy satellite or something like that, or some sort of a mission that looks at the sun, you can see that some of these orbits do go through these trapped belts, and so you have to take that into account. You have to use radiation-hard electronics or some sort of shielding to shield against these types of protons and electrons. The electrons tend to be closer to the Earth. The protons tend to be further out. Yeah. Did I get that right? No. No, I'm sorry. That's right. When I said it, I thought, no, that's not right. Yeah, the proton belts are closer in because they have higher mass, and the electrons are further out. The electrons are easier to shield against. That's the good news, and so that's why our communication one of the reasons why our communication satellites are a little bit are fairly reliable. As far as galactic cosmic rays, again, remember galactic cosmic rays come from these cataclysmic events like supernova and things like that from outside the solar system. And so you can see the relative abundance of what these are. Again, remember that what they are is that they are the fully ionized nuclei of atoms. And so the most prominent one, of course, is hydrogen. But then you have also other nuclei as well. Iron, you can see there's a little bit of a peak there. Now, please note that this is a log scale, so the power of 10 here. But the iron particle is a big nuclei, and it can cause a lot of damage, both to humans, biological damage, and also to electronics. So again, this is the number of nucleons per meter squared per square radian per second per unit of energy. And so you can see the different distributions. So the thing I want to point out here is that this is in millions of electron volts per nucleon. These are extremely energetic, some of them, and you simply don't shield against that. And you just try to figure out how to live with it. Fortunately, you don't have a lot of them. As you can see, the numbers are fairly small. So, what that means then is, for a human mission, say to Mars, what would they have to worry about the most? Certainly, this is a nice summary of all the different radiation fields that you have to worry about. Certainly, you have the galactic cosmic rays, the solar flares, and all these, but it's these solar storm protons that really pose the greatest risk to harm to both human beings and to spacecraft, the instrumentation of the spacecraft. One of the reasons why they power down the Curiosity rover when these things are coming by. So this is the one that you really need to deal with, is this yellow region right here, as far as the radiation field. Okay, so let's talk just a little bit about the radiation risk for astronauts. So, you know, we're all exposed to radiation at one time or another. Many of you have no doubt had x-rays of various sorts. When you go to the dentist's office, you put on the nice little shield, and you should feel well protected. For the x-rays, for the energy of x-rays you're talking about, that's a good shield. You wouldn't want to have that with lead. The reason is because lead has a nice big nucleus, and these protons and these energetic protons and other particles, they come in and they hit that nucleus. Guess what's going to happen? It's going to shatter. And you're going to have subatomic shrapnel going all over the place. And so the secondary radiation field can actually be more harmful than the primary radiation field in those types of things. I think Bill will probably tell you about the story where they stored in the old Skylab, they stored the photographic plates in a lead-lined container and then wondered why they were falling. And this was the reason. So, you know, as far as the risk for astronauts is, because of the exceptional nature of the occupation, then astronauts actually have one of those occupations where the limits for the radiation exposure that they are allowed to receive are higher than those for you and me. This again goes back to Council for Radiation Protection. So astronauts certainly are radiation workers, and they, because again of the exceptional nature of their work, they are allowed to receive a higher dose than the rest of it. Now, again, I threw this one in simply because this is sort of what I like. If we talk about the total ionizing dose, this is what this PID, and metal oxide semiconductor technology. Each and every one of you right now is carrying around a ton of these MOS transistors on your laptop or in your cell phone, things like that. And I'm not going to spend a lot of time on this, but basically the idea is that you have these two electrodes, the source and the drain, and you control how you control then a current path through these two things by the gate voltage that you can apply. You apply the right, in this case, positive gate voltage. The problem is that if you have ionizing radiation, you create electron hole pairs in the thing that is supposed to be insulating the gate from the rest of the semiconductor, and the electrons are pretty fast, but those holes are pretty slow, and they get stuck. Those holes have an effective positive charge. And what that basically does then is that the voltage necessary to allow this transistor to turn on and allow current between the source and the drain, that over time, with exposure to ionizing radiation, that voltage will change and shift, and that will make some of the transistors go to different operating points, which can only be tolerated so much. So transistors at different voltages now may be different than the design spec. So this is one of the reasons why people worry about effects of space radiation on electronics. The other reason is because for the same reason when a particle goes through, it also, you can see it produces these electron hole pairs. That produces extra charge. So if you have a memory cell that is storing a 1 as a data point, and you have one of these particles go through, well, it can be flipped from a 1 to a 0, or a 0 to a 1, depending on where the charge goes. And therefore, you have a data error. So they're called single event effects, because unlike this is sort of a cumulative effect from the radiation, whereas the single event effects of changing the flipping of the memory bit is due to one single particle. Okay, so let's talk about something about going on a mission to Mars. Again, depending on the mission scenario, in fact, Bill and I just had a discussion about this. Some of the numbers have been kicked around. For a 3-year mission, depending on the activity in the sun and various things, the exposure would be about a sievert. However, many of you maybe heard that there's an idea of sending a married couple to go to Mars and come back. About a 500-day mission. Now, Bill informs me that he believes that they would exceed the mission limits during that time. So you can see there's some discussion about that number, all right? Sievert is a unit of dose, what's called dose equivalent. It's in how many joules, how much energy per unit mass that's being deposited by the radiation. Dose equivalent is the absorbed dose times the quality factor. X-rays do not have as much damage on human DNA as a heavy ion like iron. That was one of the things that was trying to be illustrated here. X-rays come through, they might be able to do a little bit of damage, break a few bonds, but you can see a heavy ion, like one of those iron ions that we were talking about, can simply blow the DNA apart. So when it goes to replicate, you have a higher likelihood of getting a mutation. And so that means then that not all types of radiation are equally bad. And so that's what this quality factor is designed to take into account. Quality factor depends on the nature of the radiation. So X-rays have a quality factor of about 1, whereas neutrons or some of these heavier ions have a quality factor from 5 up to 20. So that takes that into account. One of the things that you can see from this chart is that you can see that the radiation type of environment in the space station compared to there in Mars, it's about a factor of 2 or 3 different. And so you certainly have a much more worrisome mission going to Mars than you would have for the space station. Here's some of the career limits. And it's different for males and females, mainly because, and you can see female career limits are a little lower, mainly because that's because the females have babies. And also you can see that for somebody like myself, I'm allowed the highest simply because I'm an old male. Okay, so my career limit would be higher. By the way, that mission I keep talking about, the 500-day limit, or 500-day mission to Mars that people are now talking about, they're looking for a married couple that's about my age. So, but that's for some perspective. For the general population, cancer risk increases for about somewhere between 3 to 9% for 1 sievert. Okay, to date, and Bill can correct me if I'm wrong on this, but to date, no astronaut that I know has come close to these limits. Okay. That's not necessarily, like I said, Bill and I have been talking about this, it's not going to necessarily be the case if you send somebody to Mars and then come back. Depending on the mission profile, depending on a lot of things, that certainly could be exceeded. Now, of course, we have everyday sources of radiation. I'm not going to go through all this. We get about 6.2 millisieverts of radiation per year. Now, remember, that's milli, so that's a power 10 minus 3. And the NRC, the Nuclear Regulatory Commission, there are various limits for the general public. 100 milligrams, about 1 millisievert, 10 minus 3 sieverts per year. And so, in various occupations have different activities or different limits that are allowed. But you can see that the average exposure here in the United States, about 50% of it comes from the natural sources, and about 50% comes from some sort of artificial sources like an X-ray that you might have or something like that. One of the other things that you get is you can see there's typical annual doses for various occupations. Uranium mining gives you about 4.5 millisieverts, but civil air crews is about 3. You can see that actually an air crew is almost the same as mining uranium as far as overall radiation exposure is concerned. And here this gives you some idea of radiation dose on flights for going to various cities. And again, don't know that this is microsieverts, it's 10 to the minus 6. And so it's small but measurable. And in fact, we've recently been part of a project to, you can actually look this up, it's NIRES, the nowcast of atomic ionizing or atmospheric ionizing radiation system, the NIRAD, the NASA, and it's based on various models. It will give you an indication of the radiation dose for a particular day, and then for various flights, say from Chicago to Stockholm, would tell you what you could expect for a radiation dose at that time. What we're trying to do is work with the folks that put this up to actually take measurements to help verify and to help improve some of these models. And this is actually a set of data that's taken with a TPEC. A TPEC is a tissue equivalent proportional counter. It measures absorbed dose and dose equivalent to small volume stimulated human tissue. So this sort of stands in for, this is a radiation, this is a electronic instrument you can think of as being a person. Only in the sense that you look at the absorbed dose to its relatively small volume of simulated tissue. And so this is for a flight, happened in 2011 at night, and you can see where you see the ascent, relatively level flight, maybe they had a change in altitude, and you can see the descent, maybe a little bit of turbulence on the way down, and then there, but you can see very clearly, you can see that there is an increase in the overall radiation absorbed dose rate during the flight. And so some of the work we want to do also is going to look at the electronic effects, but we're in the process right now of putting together a suite of instruments that will go on board different aircraft to measure, help measure some of this stuff at various places throughout the world. Okay, so I do experiments. I'm not a modeler. I do try to do actual measurements with things. You want to talk about radiation modeling? One of the world's experts is right here. You can ask him. But we're doing a lot of experiments. In order to do experiments, and the energies of the radiation you're talking about very high. Therefore, you have to use some very large instruments to do this, very big, to get these energies that you need. You can look at doing radiation experiments on space. The problem is this: time. You have very low fluxes in space, and it costs about $1,000 a pound to put something on the space station. So we use these accelerators to simulate the radiation environment in space. And so basically what that does is particle accelerators have the general effect of compressing time, meaning that the flux of radiation of particle accelerators is much higher than what you get in real space. And so, for example, if you look at one of the places where we go and do various experiments is the Los Alamos Neutron Science Center, 1 hour of exposure to the beam at this facility is about equivalent to 300,000 hours at 40,000 feet. So you can see the whole idea is then that these accelerators with a much higher flux have the effect of compressing time. This is just some places where we do radiation experiments. There's a facility at Texas A&M. The ones that we've been using the most recently is the one in Los Alamos, looking at neutrons. Also the Space Radiation Laboratory in SRL, that's the Brookhaven National Lab. The Loma Linda Medical University, they have a proton facility that's used for cancer treatment, similar to the cancer treatment facility that's found in MD Anderson. And we also now, just recently, we've installed an X-ray source at Prairie View. Nice thing about the X-ray source is you can turn it off. It's relatively small, and so we can do some of the initial total ionizing dose experiments right in our backyard. Also, some of the facilities that we use, in talking about space radiation, well, there are other radiation environments that some people are interested in. For example, nuclear weapon type of environment, and we've done work with that at the White Sands Missile Range using flash X-rays and things like that. So typical radiation experiments that we do, again, we have this beam of particles that come and from the accelerator. and those simulate various aspects of the space radiation environment. Sometimes you just want to irradiate a piece of material and see what happens to that material compared to some control samples. Those are what we call point and shoots. Those are the easy ones. Then we also do experiments where we use the beam and actually expose the electronic devices and monitor their performance as it's being irradiated. That's the ideal thing to do. Sometimes you have to do a sort of before and after type of thing. That's one of the types of experiments that we do. And another typical experiment is doing a shielding type of experiment where we have some sort of intervening material. Here's that proportional counter that comes again, picture equivalent proportional counter. So that would be our human. We also have proportional counters that simulate electronics and things like that. So we looked at how well the intervening material, how well it ameliorates the effects from the radiation beam using this type of experiment. So this is some examples of some of the data we've taken over the years. This is for a radiation shielding experiment. This is at 1,000 MeV per nucleon iron ion, so this represents a galactic cosmic ray type of environment. And the interesting thing about this is for this particular ion, what you see is here's the absorbed dose for various thicknesses of material, and there's different materials. This high-density polyethylene is this curve, and that's sort of the gold standard that people use because it's one of the things that if you're going to make a storm shelter on something like the space station or on this 500-day trip to Mars, you want to maybe use something like polyethylene because it has a lot of hydrogen. Hydrogen atom molecule, the hydrogen nucleus, if you hit that, there's only one proton in there, so you don't get this shrapnel, subatomic shrapnel. And so it's good to use where low Z or low atomic number types of materials in your space radiation shield.
Richard.
Yes.
During solar minimum, there is higher incidence of galactic cosmic rays reaching us. I believe that's because there is less hydrogen from solar winds way out in our solar system rather than due to magnetic effects.
Well, but I think that the reason why that is true is because of the magnetic properties of the sun itself. I'm not an expert in that.
Well,
so.
I'm just repeating what I've read.
Yeah.
Okay. One who studied particularly at university is that the higher solar magnetic field during high activity deflects more of the cosmic rays away from the inner solar.
And that's how I've understood it.
Well, I still believe it's because there is more hydrogen solar wind out there during solar maximum. Thank you.
Yeah, I think there's a concept that maybe that solar, the solar protons sort of push away or sort of prevent I'm not exactly sure what the general model is for that, but again, I believe that it's the activity at solar maximum, you have a higher magnetic activity, and that helps to deflect some of the galactic cosmic rays from reaching in towards the Earth. That's my understanding. Interesting thing about this is that you have, here's the shielding from the performance of high-density polyethylene, but I want you to notice that for something like aluminum, the shielding is not such a good shield. Again, it has to do with the fact that the aluminum does not do as good a worse job in producing these secondary particles that then actually increase the absorbed dose and dose equivalent that is measured by the TPEC.
Rick, you've got one green point for the Pika.
Mm-hmm.
You just had one data point?
Yeah, we only had one signal.
And I'll talk to you what's up.
Yes.
Sidebar.
Okay. Okay, so what I want to talk to you a little bit right now is some of the stuff that we've done with what are called Bert and Ernie. These are lunar and Martian regolith systems that we have used, simulated lunar regolith and simulated Martian regolith. Again, the data, this is based on actual Apollo 11 samples. So this basically has the correct chemical composition and essentially the same grain size and things like that as actual lunar soil samples that were brought back from Apollo 11. And this is what's called JSC Martian 1, which is a Martian simulant. This is based on data that was first obtained by Viking landers back in the 70s. And so, of course, that new data is coming in, of course, from the rovers. But this is what is currently used as a simulant for the Martian regolith. Regolith, of course, is just a fancy word for this.
How long are these simulants that are running?
How long these particular ones, or how long?
No, in general, the composition of Bert and Ernie, how long have they been established?
The compositions for these have been established. Well, I know that the JSC-1A for the lunar stuff has been around 20, 30 years. I don't know about the Martian stuff. I'm not sure about that. But those have been available for a long time.
The reason why I ask is we have a guest speaker who has having here was talking about the hydrology of the moon, and apparently there's more trapped water in the regolith itself that was only recently been confirmed.
That's right.
Which would be more hydrogen.
That's right. As a matter of fact, I took those slides out. We did some experiments where we took the regolith, put in, made sure it had the right amount of water in it to see if there would be an effect from that. There is a measurable effect, okay, that you can observe. So the water that would be in, say, some of the crater areas on the South Pole and things like that, if you use that to make a storm shelter or some habitat on the moon surface, you'd actually get, because, like you said, because of the higher hydrogen content, it'd actually be a better shoot.
This was actually in the samples that brought back, which weren't part of those.
Yes, I know. That's been fairly recent. Yeah. That's in the last couple of weeks, I think.
It's still the case that lunar material is very, very dry.
Yeah. That's certainly.
There's more water in the lunar material than they used to think. It's
Yeah.
not very much.
Yeah. Well, of course, these are sitting around in the back of our loading dock. So but basically what we had to do is dry them out first and then put the right amount of water that we wanted to in to do those experiments. So the idea then is to use these, to make ground-based experiments be as realistic as possible using these regoliths. And so the concept is really very straightforward. Here you have what's actually going on, space radiation coming in, you have the atmosphere, you have the surface, you may want to bury some of the, things to take advantage of using the regolith as shield. So the idea then is that we have, for the particle beam experiments, we have particle beams that would be simulating space radiation. For example, we use a block of dry ice, not that thick, that simulates the atmosphere of Mars. Here we're putting it installing it in one of the very first experiments. You want to wear gloves, okay? Yeah, and so then you have various experimental zones. So the surface, you have a buried zone, another sub-buried zone, using various thicknesses of the regolith. And you can modify this concept for asteroids or other planetary surfaces or even spacecraft structures. So that's our Ernie concept. In fact, we just recently, in April of last year, here's a couple of students that are working at the Brookhaven National Lab. Again, you can see there's our Martian atmosphere. We did indeed wear gloves when we put that in there. And then here are the regolith samples that they're using. One of the things that we're looking at is using the regolith as making materials once you get there, using something like polyethylene as a binder. This is a sample where you use polyethylene as a binder with the regolith that's going around. So you sort of call this lunar adobe. And here we have the Martian adobe. The students here are working on the Martian adobe and looking at, you can see various thicknesses of this Martian adobe to look at the radiation shielding properties of that material. Let me pass that around too. This is a graph. This is actually experimental data. This is loose regolith. Just Martian regolith like you're being passed around here. Then you have protons, these are 200 MeV protons, and this would be indicative of a solar proton type of environment. A certain thickness of the regolith and the T-Pec, again, this is our astronaut. And we compare this, in this particular case, compare this to the high-density polyethylene, and you can see that they're roughly the same in this environment. What that means is that the regolith would make a good, relatively good storm shelter on the Martian surface, is what the data would be indicating to you. So again, this is sort of just an example. This is the lunar type of environment. Again, just the idea that you're trying to simulate some real things that are going on here. The T-Pec again represents our astronaut. Here's our little shelter that is set up using some of the material that is being passed around here. And you can see we have a buried habitat where you bury it underneath a lot of this stuff. And then you have the surface habitat where you have a lot of stuff behind it, and et cetera. And so we've done a lot of combinations of that. This is just some example results that we got from the material land. One of the things I wanted to point out is that if you look at the surface habitat with if you just look at the dry ice, you can see that the absorbed dose goes down by about 40%. That's almost as good as having a thickness of the regolith about that thick. So CO2, the Martian atmosphere, while it's not very thick and it's very much thinner than the Earth's atmosphere, still pretty good radiation shield. Still pretty good radiation shield. This is another graph using, instead of the similar type of regolith samples like the lunar ones. Again, this is lunar. This is compared to both high-density polyethylene and aluminum. This is 80% regolith, 20% high-density polyethylene. You can see that, again, for at least for the 200 MeV protons, meaning the kind that would come from the sun, they're very much the same. That's good news because that means that these types of materials could indeed be used for a storm shelter on the planet's surface, or on the moon's surface. This is one of the things that we also do is we dose these things to doses that are commensurate with what you would actually experience and see how that would affect the material properties. What we find is that for doses that are commensurate with what you would actually see in space over, say, a 10-year mission or something like that, you actually increase the material strength maybe a little bit. You get about 10% or so error on this, so the error bars are pretty close. So you don't, space radiation really doesn't affect the materials all that much, bottom line. This, however, this is a piece of a fan that was exposed to about 800 MeV of 800 megarad of gamma rays. This was at the White Sands Missile Range. They went in, they heard a noise in the morning. They were doing a very long exposure, a bunch of noise. They went in, saw that one of the fans was damaged, went over to pick it up, and it just crumbled in their hands. So space radiation may not have so much effect on materials, but radiation will create broken bonds in materials, and therefore when those bonds come together, sometimes they come together in such a way that makes the material more more brittle. And so feel free to break that apart as much as you want. But you can see that it's brittle enough so that even a small piece is easily taken apart. That is a very, very high, that's the most highly dosed piece of material that I've ever come across. And no, it's not radioactive. This is a manifestation of Bert and Ernie, kind of all made up in this nice little plexiglass thing. Again, this is, I'm not going to go through all of this, talking about all this. Again, our T-Pack is our stand-in for our astronauts. And again, you can see we can have various ways of configuring this. One of the sort of interesting experiments we did a couple years ago, and most recently in October, we redid some of this experiment, was we actually looked at using cells. These are human blood cells that we then used in this type of environment. Here you have the surface habitat. You have a guy standing on the roof. You have a couple of people in here. You have then some of them buried beneath the regolith. And then, of course, this is a bulk of the moon's surface. And here's the team did it. There's the schematic. Here's the implementation. The beam, neutron beam coming in this way. And believe it or not, it actually does what you think it would do. The amount of abnormal cells that were observed, most of those were from the person on the roof, got the most exposure, and you can see it went down very nicely with the more shielding we had. So that was actually very good news. Like I said, this was sort of one of those experiments where you said, well, we have some leftover cells, let's see what we can do. We did a little more rigorous experiment in October, and we're still analyzing that data. Nice thing about this dirt that we have is there's just something about dirt. We've had a lot of good outreach experiences with this. Here, my son was a Boy Scout, so I was talking to Boy Scouts. We have students coming, except for this guy, he wasn't terribly interested, but have some real interest. We had a 3-star general who was in charge of the Star Wars program come through. And, he had a whole entourage with him. He comes in, he kind of, and then I opened up the big bucket of lunar regolith. And it was like a kid at Christmas, because it looked like you immediately start to play. So we had a 3-star general playing in dirt there in the lab, and he really enjoyed himself. So there's something about dirt. So these are some of the acknowledgments. Again, a lot of this work is very multidisciplinary. I'm a physicist. I've worked in an engineering department. The nice thing is, I've always found it, and I understand many of you are physics majors, you will find it relatively easy to talk to most engineers. Okay? So I have chemical nuclear engineers. I have, again, physicists. I have mechanical engineers I work with. I have chemical engineers I work with. Those guys are relatively easy to talk to, the engineers. It's the biologists. The biologists are really tough. They speak a whole different language. Over the years, that's been a real challenge. The engineers, though, not so bad. So you physicists that go out there, don't worry about the engineers. You might want to brush up on some biology. So I just want to say thank you. Again, many of these are actually not staged. You can see that sometimes we have to build things in hotel rooms and get things ready. Again, a lot of this is just building up some of these targets that we use for the various experiments we do. But again, what we emphasize is we emphasize education through hands-on research, and that's been very useful to our students throughout the year. Right?
Oh, I just wanted to point out to the undergraduate students that
you know, a lot of people do go from bachelor's degrees in physics to master's and PhDs in engineering.
Yes, that is true. They come through my classes, okay? Especially graduate students, physics graduate students. They'll have to take some remedial electrical engineering courses in order to go on for the MS or PhD in electrical engineering. Almost universally, they are the best students in my class. So, but yes, he is indeed correct. There's no reason why you cannot use your physics degree to go on to an engineering degree. No reason at all. You have all the basic stuff there. All right. So it's certainly possible. I will be happy to entertain any questions you have. Yes, sir.
That 25 grams per centimeter thickness of Regolith you were using as a shielding model,
Yeah.
roughly what linear thickness is that?
That's all I have. Yeah, because the density I think is 0.9. It's a little bit higher, I believe, than aluminum. 2.7. So, yeah. It's about.
Is it compressed Regolith or is it liquid?
It's just fluid. What I had there was just fluid. And in the sense that it's packed in the sense that like you would pack flour for a cake or something like that. We don't do anything for the loose Regolith. We don't do anything in particular. For the panel that was around, that's mixed with the polyethylene, and then that's compressed and heated at the same time to make that walk. Yes, sir.
In reference to radiation effects on electronics, with some of the new compound semiconductors, they pretty much the same problem, like the gallium arsenide.
Don't have the data on in the slides, but we're doing some work with silicon carbide. Okay, silicon carbide, the power MOSFETs that we're using actually do show these kind of shifts under the exposure to the X-ray. This is one of the first experiments we started doing with the X-ray. And so for those total ionizing doses, and that's in the order of about 50 kilorad, 50 to 100 kilorad, you start to see those shifts. Now for silicon, for a comparable silicon power MOSFET, you start to see shifts at maybe a kilorad or so. So they are more radiation tolerant.
Is it more substrate related or is it the dielectric?
It's the dielectric.
So what about sort of the nighttime?
I don't have any direct data from silicon nitride, but I would think that silicon nitride would probably be as tolerant, if not maybe more tolerant, than silicon carbide. That's a guess.
Just a quick question on the solution to radiation hardening. Is it to reverse the increased density as one what type of way to improve your electronic stability? Is it to not go to the smallest transistors possible, to go larger transistors?
Yeah.
Or is it looking for material changes?
It's a little bit of both. It's also different types of structures that you use for the devices. They use what are called radiation hardening by design techniques to try to come up with device structures that will, for example, take excess charge and pull it away from the sensitive area in the circuit. That's one method. But the problem with that is, of course, that you're taking up real estate. You're taking up space. It costs money to do that. And it also costs performance. The ideal thing then is to use what are called commercial off-the-shelf things, just like carrying around your cell phone. And in this sense, you have a couple things that are competing. Number one, you're making these things smaller so they're smaller parts. But on the other hand, you're also making the overall charge that's needed to, say, store a 1 or a 0, you're making that smaller. And so you have two competing things going on there. And right now, it seems, we went through a time where the smallness was helping, but now the smallness seems to be hurting.
That's what I was trying to say.
Yeah. The most recent data, every July I go to what's called Nuclear and Safe Radiation Effects Conference. That's where the geeks go that worry about the radiation effects on electronics. And in the last few years, that's sort of been the trend.
There would have to be some sort of break-even point where
Yeah, I think we've sort of gone beyond that. Now the smallest is been a little more harmful. Oh, yeah.
Okay, looking at the effects on astronauts, do you look at the total body exposure, or do you have like certain critical margins?
In fact, and this is not my area of expertise, but they are considering the dose, the different risks from different doses based on different organs. The truth is, when you send somebody up there, they're going to get, you're going to get a whole body type dose. But yes, there is more worry about where the dose goes. But again, it's not like the treatments that you would get for cancer. I mean, it's where it would be directed.
Each critical body organ has a different radio sensitivity. And there's
well, see, some of the risk assessments now that they put together for astronauts are based on considerations for different organs.
I think you showed, as I recall, the BFOs, blood-forming organs.
Mm-hmm.
Those are the most critical. Again, the eye and the skin are susceptible. The skin, out of geostationary in a space, you really get toasted skin.
Now with the software, where it's like it changes bits within the memory storage.
Mm-hmm. Yeah, that's a hardware issue.
Yeah. I mean, well, it seems like it's also to be fixed with the software.
That's right, and they have different types of code that looks for errors and incorrectness.
Yeah.
And the issue, some of the issues that are coming about now is that you have one of these particles coming in, the devices are getting so small that it affects more than one cell. Okay, so you have these multi-cell type of things, and so then you can overwhelm some of the software things.
But it doesn't go through it goes across the top of the circuit or something like that.
Yeah, that's right. The grazing angle.
Grazing.
You have a grazing angle. Yes, ma'am.
So it was interesting that a couple of years ago, French daughter did some research on correlating the astronaut effects or health effects in the solar cycle, and it turned out the one with low activity actually was more health damage. That's what I remember, but they didn't explain why. So I think today what you mentioned is probably kind of anything, maybe that's the reason, because we have more PCR coming.
That would be the only thing I could think explanation for that. Is that because of the fact that
Because I was shocked and I didn't know that there was no explanation.
Yeah, that would be the most. I would think that would be the most reasonable explanation. Because then you have more GCR things. GCR, as I said, the protons you can shield against. The GCR you really can't. And the GCR, especially if you have some of the heavier ions, can do some real damage to the cells. That's a likely explanation.
Have you talked to the U.S. professor trying to heat up the dirt and moon and make the solar panels? So.
Yeah. No, not what's his name?
David Crystal.
No, the guy from the Russian guy.
Alex.
Yeah. I know who he basically trying. The idea then is you take the regolith and then you can make things like solar cells, things like that from it, and use the materials for different institutes. Alex,
It's not.
yes, but the answer is yes. We're sort of going looking at the.
So maybe you can integrate that and also the 3D printing for the.
Yeah. Yeah, I mean, the whole idea is that you would maybe send some robots ahead of time that would just scoop the stuff up and process it in various ways, and then sort of lay it out for you for the next robot to come and maybe build a shelter with it, or maybe some solar panels. Now, solar panels are a little harder. I mean, it's one thing to take a bunch of dirt and take some plastic and mush it all together and make it a brick. It's a whole other thing to make a solar cell.
But there's a building came up with a process of microbead of the silicone instead of.
Yeah, that's right, I remember that. So, yeah, it's sort of a quick and dirty type of thing, yeah. I'm sorry. Yeah, you go ahead.
Something about making these panels by impregnating the solid as a plastic. Are you familiar with Larry Taylor's work at the University of Tennessee, where he takes lunar regolith and microwaves it, and the iron absorbs the microwaves, and you basically can create blocks, solid blocks.
I have heard of it. Yeah, this is something, well, this is more straightforward. It's basically take stuff, mix it up. You compress it, heat it up. But yes, I am aware of that. No. We haven't done any experiments with that. So another thing to remember is that so the energies of particles that you're talking about, you know, the processing is not going to have a lot of effect on the chilling effect.
Yeah, the idea is that you don't have to bring any material to them and see that.
Yeah, I do. Yeah, that's right. Just use it there. Because it will cost money to take stuff there.
It's kind of funny, I heard that the roach is the gas hazard.
The roach? Oh, yeah. That's right, he survived a nuclear war. That was the old joke, right?
So it's still in hazard. Fire.
Yeah, it's a simple thing. Basically, simple things tend to be more radiation tolerant. And so, you know, the roach is a simple organism. No questions from the students? Come on.
Well, okay, I'm going to say up front, this may be dumb.
No.
But out of this whole thing, it's purely out of curiosity. You have a slide about DNA and how the solar photons would essentially mess with your DNA and break it apart. I was online with the question asked to several scientists, and they didn't know the answer. And I think you may know. The question was, if you went to the LHC and put your hand in front of the beam, what would happen? I mean, that may sound dumb. That may sound dumb, probably. But solar photons are being used, they use photons for the
Now, let's do a couple things. First of all, those protons are extremely high energy. So, the amount of energy that they would deposit, if you just put your hand in there, would be extremely small per unit proton, per proton. Okay, so those things are buzzing along very, very fast. They're very relativistic particles, right? And so the amount of energy that they would transfer to your skin and to your bones and whatnot in your hand during the time that they crossed it would be exceedingly small per unit proton. Right? So it would depend on the flux. How many protons do you have? Of course, if you have a lot of them, you depositing a little bit, then he's right. Maybe it would be enough to cause some real damage. Yeah. But again, I don't know what the energy guys call luminosity. I'm not sure what the luminosity or what the flux is at that. My guess is if you just probably wouldn't do anything.
Yeah, really. Wouldn't it also depend on where? Isn't the range of photons more related to energy? So it
yes.
Depend on where you position your hand?
No, but it would depend on where, if the beam is coming at a particular energy, then you're right. The amount of energy that it would deposit would depend on the energy itself. Now, I'm not sure what you mean by where, because if the beam's coming in and the beam is the same energy all along the path, then it really wouldn't matter where along the path you put it.
I was thinking if you have a 250 MeV proton beam, it has a certain range. If
yes.
you position your hand right at the end of the range, then that's what's going to release most of the energy.
But the thing is, the reason why it has a range is because it's going through material. If it is going through vacuum, okay, now you're right. You have to, in fact, when you do cancer treatments, you're relying on what you're talking about. Because what you want is that most of that energy deposited where the tumor is, right? And so if it's in the somewhere in the middle of my brain, then you want the energy of the proton that hits my skull, you want that energy to be high enough so that it goes through most of the tissue in there without depositing very much energy at all. But it's going to. So it's something called, there's a concept called Bragg peak, right? And so the more material we go through, the more energy that's deposited, the proton slows down. The more it slows down, the more energy is deposited. The more energy is deposited, the more it slows down, the more, and all of a sudden there's going to be a sudden deposition of energy where it deposits most of its energy. You want that sudden deposition, you want that to be in the tumor, not in the surrounding tissues. Okay? And so the proton therapies that they do at Loma Linda, they do here at MD Anderson, they rely on that. But as far as the beam is concerned that he was talking about, if you have this whoppingly high energy beam, and you put your hand in it, well, it's going to deposit some energy here where it enters, but it's going to be going so fast and so quick through there, it's not going to have a chance to deposit much energy in that thickness of human tissue.
What's going to happen? The large number of people whose English is not their native tongue will descend upon you and drag you out of it. I'm walking late to this turn where I'm not supposed to be in.
What's the production cost on the hot effect? TPP?
What is the what?
The production cost.
That hot defect costs about $35K, but their throughput is like one company that makes these things, and their throughput is not very high. So the idea is, Bill and I were going to project, the first idea that these guys have is you take one of these hot defects, you basically put it on a carry-on suitcase and put it in every commercial flight in the country, right? You can't do that. Even if you have the $35K, these companies simply wouldn't be able to produce enough for you to do that.
Because I noticed you had a section circle and had it, you were like, the cause be turbulent. And I was just curious if you had performed any experiments where you actually just shake the thing.
Yeah, as a matter of fact, we haven't. So it's entirely possible that some of that noise that you see on that data is just from vibration.
Okay.
Because how the CPAC works is a volume in there where there's a small wire that's an anode. And sometimes the vibration will vibrate that anode so that you get noise. Any other questions? Yes.
In your plastic Regolith, you mentioned the Regolith helps protect the plastic from little.
I don't, I think that the plastic, when it's irradiated, the plastic will have a tendency to bond up a little more, and it actually makes it a little stronger mechanically. So it's kind of the other way around. I think it's more of the plastic helps bond the material and also makes it more radiation tolerant. Yes.
Just something that I got informed of when working with the automated spectrometer project. As you say, a lot of composites actually get stronger with radiation exposure, but their creep profile changes.
Yeah.
And that's basically the two effects you'll see.
Yeah, and so that would be very important for the instrument like that. Did you have another question?
Oh, I was wondering if you mentioned, I can't relate, did you mention about the linear effect that is known in proton?
You mean linear effect from
because
the dose?
More paths, longer paths than the slower.
Yes. Well, that's right. So when you slow it down, then it takes longer for it to go, and it takes longer for it to deposit more energy. And so the dose is higher.
Yeah. So how do you take that into your design of the shielding positives and negatives?
Well, the effect of the design, then you look at various thicknesses to see where, at what density thickness, you start to get the increase in you can see in some of the proton experiments where you see it actually climbing up the Bragg peak. So when you get higher thicknesses, it'll slow down the proton so that when you look at the absorbed dose on the other side, it actually starts increasing. And that's why, because as the shield thickness gets thicker, it's slowing down more, the proton's slowing down more to go through, so when it goes into the CPAC, it absorbs, it deposits more energy and therefore goes to the body. And so basically then what you do is you try to design the experiment to look at you can't use all the different energies that you experience in space, so you just try to pick a typical energy and then look at typical thicknesses. And then basically what you do is you do an inner comparison. You compare the one type of material against the other. And so see if it would be better or worse, depending on how it would fragment under that radiation. Basically, you're looking at the secondary effects, secondary radiation. So you're doing a comparison, more of a comparison between different materials. Yes, ma'am.
And just answer that person's question about the dirt and the plastic, and whether the plastic, prevent it from becoming brittle, means the dirt. I would be surprised if they worked both ways, because that's not the primary purpose of making the plastic and dirt brick, because there's some research that shows this inclusion of small amounts of sodium clay and polymers help regulate the cross-linking over time and prevent polymers from becoming brittle. When you perform sort of regular tests, like tensile testing and stuff like that, not too personal.
Well, that's interesting. I wasn't aware of that.
Any other questions?
Yeah.
Are there any shields that kind of rely on electromagnetic properties?
That's called active shielding. And so there have been studies where you would use, basically use coolant loss to try to deflect charged particles, like lightly black Gaussian rays as polar protons. And, I don't have a picture, but they show these very large metal spheres that are at a certain potential that then, you have a collection of them that then would set up a magnet or a static electric field that would help do this sort of thing. And they've even looked at doing it on the surface of the planet and also in spacecraft. And the problem is you're talking about things that are really big. And you're talking about potentials that are really big. And so right now, it's not practical to do this sort of active showing like you're talking about. But, basically we know it works, right? Because it works for the Earth. Because that's essentially what the Earth has is going forward. It has the passive shielding of the atmosphere, but also has the active shielding of its magnetic field.
Have you gotten exposed to Regolith Samuel team's design for magnetic shielding based on the magnet design that he had originally used for the method?
Yeah, I'd heard about that for the that same instrument, right?
Yeah.
And again, I think it's a matter of size, though, isn't it?
Yeah. It had a limited size for the crude volume inside. It also had a problem as a safety engineer. I had a problem with it that if anybody went EVA, you get a double dose. It became high, and they get bounced back.
Okay.
But you didn't really need it.
Yeah, it's big. To put that sort of mass.
Mass was the issue, but when he showed the comparative between the similar mass of passive, it was actually far less.
Yeah, well, this is one of the reasons why the radiation biologists, they look at ways to just make humans more radiation tolerant, essentially. And that's not easy either. Basically, eat more strawberries, more blueberries, more antioxidants. Yeah, blueberries.
This regular shielding, does that also work on things like
Well, it could help because there's a lot of the biggest component of the lunar regolith is silicon. That's one of the reasons why you talk about using it for solar cells and stuff like that. It's basically most of silicon. And the reason for that is because there's a spot that one time in the moon was part of the Earth. And of course, one of those common elements on the first surface is silicon. And so there would be some way that there would be a certain amount of conductivity that would be associated with that. And certainly with the iron content in the Martian surface, I would say that also could probably be used for electromagnetic shielding. If that's what you need to do. Usually you have sort of the opposite problem. You want to get your signal out, which any other questions? Well, I very much appreciate your attention. Your questions. It was a lot of fun. Thank you.